Okay, so we've reached a point in our development of this post-Minkowskian theory where we have set up expressions for the wave zone gravitational fields. We also talked briefly about the near zone fields, but I want to focus on the wave zone fields because ultimately we want to talk about the nature and properties of gravitational waves. So we started out with this just very simplified scalar picture of a wave equation, a flat space-time wave equation on psi given by some source mu, but mu consisted of both a material part, the masses, the sources, but plus also a part that extends over all space. And for points in the far zone where x, the distance to your detector, is large compared to the size of the near zone, we could expand in the small powers of this and get a multiple expansion. So we have products of x prime, x1, x prime I, x prime j, x prime k, and then derivatives of this source at a constant retarded time, t minus the distance to the source, to the center of mass of the source. And so the near zone part of this integral was given by this general expression, an infinite sum of multiples of the source density mu. So now bring back the indices, and now we're talking about our fields h alpha beta, from which we're going to get the metric ultimately. Then we get a similar kind of expression, the overall factor, derivatives, multiple moments of now it's the tensor source of the gravitational waves, but evaluated at a fixed retarded time t minus r. And now I want to just explore the general nature of these far zone fields, starting with H00. So now we're going to look at a sort of component by component to see what these things look like. So let's look at the first, second, and second terms of this H00, and then just look at the sum from L equals 2 to infinity. So the first term is just, there's nothing, it's just integral of T00 integrated over the near zone with 1 over r in front. Well, what is the integral of T00 over the source, roughly speaking? Sorry? Energy, or just the mass of the system, right? So this looks just like m over r. Let's see if I want to bring it up. Yeah, so this first term is just m over r. Well, that's exactly what you expect. At the leading order, the metric should look just like, gm over r. Of course, we have to construct from this the actual physical metric, going from that Gothic metric. There's a bit of algebra to do, but so far so good. We get the kind of Newtonian potential m over r times g. Then we have a term here that looks like, excuse me, there's a gradient, but there's T00 times an x integrated over the near zone. Remember, I showed something that looks something like that. It was the center of mass of the system. But this is what it should look like, right? It's the distribution of mass times the location of each mass, summed over all the masses are integrated. So that's the center of mass. And you know that the center of mass, we can actually verify it from the conservation laws I talked about earlier, but generally speaking, for an isolated system, the center of mass moves uniformly. It's never accelerated unless there's some body out there accelerating it. It moves uniformly. So you can always find a reference frame in which you're moving at the same speed, so it's at rest. You can always translate your coordinate system so that that center of mass is the center of your coordinates. And so the center of mass is 0, and it's always 0. Okay? So basically, this term can be just tossed. It's the center mass, and you can always set it equal to 0, and it's going to stay 0 because of the conservation of linear momentum. And so then we have a bunch of multiple moments contributing to this H00, beginning at the quadrupole moment. L equals 2 generally stands for quadrupole, so it looks like the mass density times a product of 2 x's integrated over the source. So basically we have Newton's theory, m over r, the leading term in the static gravitational potential, plus something that involves the quadrupole moment. Oh, I did have something to show. M and center mass equals 0. Okay. And these are just multiple moments. We'll call them I. The index L just tells you how many x's you have. So it's the multiple moments of the source density. Okay. What about the space-time component, H0J? So J is the spatial index. So we have a similar thing. There's the first term, the second term, and then L equals 2 to infinity, all the rest of them. So it turns out that these, if you remember that partial derivative of this tau alpha beta with respect to beta vanishing, again, because there are partial derivatives, this gives you some very nice identities that you can exploit to simplify these expressions. Well, in this case, of course, this is just the momentum of the system. T0J integrated, it's just the total momentum. And again, you can always put yourself in a frame that's moving with the same velocity as your source, and so the total momentum vanishes. So this term you can throw away because you can always make it zero by your choice of reference frame. But this term, there's a particular identity. Remember this partial derivative of tau alpha beta. You can write down this identity. Takes a little work, but you can do it. That this product, tau 0j xk, is equal to a time derivative of this, which looks like a quadrupole moment, an anti-symmetric combination of x with the momentum density. Those square brackets mean an anti-symmetric combination. So it's tau 0j xk minus tau 0k xj. So it's anti-symmetric. And then something that is a partial derivative of some other junk. Well, remember, we're integrating over this near zone with respect to d3x, so this partial derivative just becomes a surface integral. Now, whether or not you keep that surface integral depends on whether it depends on the radius of the near zone. It may be canceled, but you have to pay a little attention to it. Turns out at the end of the day, you can ignore it. You can forget about it. It is zero. So all you have to worry about are these two terms, and when you work out those details, it turns out that this produces a constant term in the H0J that involves the angular momentum of the system. Now, the angular momentum of the system is itself constant. Remember, we talked about conservation laws for total angular momentum. So this is just a constant piece of the H0J that depends on the angular momentum of our system. But notice it falls off as 1 over r squared. Okay, sometimes this is called the gravitomagnetic part of the potential for gravity, in analogy with the magnetic part of the vector potential for electromagnetic theory. Then there's a term that involves this piece, and again, it's this quadrupole moment of the system. There's a time derivative of it, but really it's just the quadrupole moment that contributes. And then we have the remaining stuff summed from L equals 2 to infinity. And the final piece is the space-space part of the field. So it's just tau jk times L products of these x primes and L partial derivatives. Again, it's a constant retarded time. And here there's another identity that you can exploit, again, because this partial derivative condition acting on tau that says that tau jk, it turns out to be 2 time derivatives, again, the same quadrupole moment object that we saw before, plus a divergence of some other junk. Once again, this divergence integrated can be converted into a surface integral, and we throw it away. Again, you have to sweat a few details, but once you've done that, you can convince yourself you can throw that away. Not that it's zero, but it depends on R, and it's going to be canceled by stuff from the outer integral, and you can actually show that. So that surface term vanishes, and again, you're left with something that involves the quadrupole moment of the system. So this HJK is 2 time derivatives of the quadrupole moment of the system divided by the distance, and again, summed over higher multiples. So just to kind of summarize this sort of general structure, and here we make use of a bunch of useful identities, just products of the distance r and the unit vector in the radial direction. So the gradient of the distance is equal to a unit vector, gradient of 1 over r is this, and so on. So there are lots of products and derivatives of things that are useful. Notice the gradient of proper time is minus the unit vector n over c. Remember, tau is t minus r over c. So the gradient of tau, because it's a retarded time, not just a pure time, also gives you a unit vector. So H00 is just a constant piece that's related to the Newtonian potential, plus these derivatives of multiple moments starting with the quadrupole. H0J is this is just what I wrote before, but if we really focus on the 1 over r parts, remember we want to look very far from the source where our gravitational detector sits, so this term falls off as 1 over r squared, so it's going to be negligible by the time we get to our detector. It's only the 1 over r parts that we care about. So here we get quadrupole moment divided by r and higher moments here. And HJK, again, just the 1 over r part is 2 time derivatives of the quadrupole moment at higher moments. So notice that in the sequence of terms, the leading contribution is a quadrupole piece. Apart from this just Newtonian potential, there's an L equals 2, there's a quadrupole moment here, quadrupole moment there, and a quadrupole moment there. We can kind of summarize this even in a more simple manner just by writing down very generally what these fields very far away from the source look like. The standard Newtonian piece, a simple function of retarded time and direction. A spatial part of the metric is a vector piece depending on retarded time and direction. The HJK is a tensorial piece with the same kind of dependence. Tau is t minus r over c. And this is the leading 1 over r part of the field far away. And the fact that these things satisfy the Lorentz gauge or the harmonic gauge, so the time derivative of that is equal to the divergence of that, that tells you that c dot is equal to a unit vector times dj dot plus corrections that fall off with 1 over r. And the time derivative of that is equal to the divergence of that, tells you that this time derivative is equal to nk times that time derivative of that. So these functions are strongly related to each other, and you would have thought that there were, I guess I don't want to say anything more than that, but there are strong links between these functions and each other. And the result of that is that when you want to ask what is the behavior of materials far from the source when it's impinged upon by this metric, by the gravitational waves that are being emitted by the source, how does the system behave? And there's several ways to work this out, but one is called the equation of geodesic deviation. It tells you how, if you have two particles that are just moving on geodesics, moving freely, not attached to anything, not acted upon by any forces, and how do they behave in a given gravitational field? And one way is to ask, it's pointless to ask how does one particle behave, because it moves on a geodesic, which in a freely falling frame is just simply a particle at rest in that freely falling frame. So that doesn't tell you anything. What you really want to know is what's the behavior of that particle compared to another particle nearby. Each particle alone is on a geodesic, but what happens to those particles relative to each other? There's a particular way of working that out, and that's to consider one particular geodesic that's moving through space-time like that, then consider a nearby geodesic moving through space-time like that, This fiducial geodesic has a four velocity u, that's the tangent vector to the world line. So that's the velocity, four velocity of that particle. And then define a vector that connects this particle to the nearby one, that vector is called xi, and ask yourself, how does that vector change as time goes on? And there's a very particular way to make that connection, to define that connection in a very specific way. So in particular, how does that change? Does xi grow with time if the particles are moving away from each other? Does it shrink with time if they're going toward each other? But more importantly, does it have a second derivative with time? Are these particles accelerating away from each other? Or are they accelerating toward each other, right? That seems to be a more significant product than if they're just have a relative velocity, because that just depends on their initial conditions. If I started them off going away, sure, they're going away. But I really want to know is, are they converging toward each other or are they diverging? So you can work out precisely what happens to this vector xi, what is its second derivative with respect to, say, proper time along this fiducial geodesic, and you can work out what that is. And it turns out it's proportional to this famous Riemann tensor that I talked about very early on, the beginning of my first lecture. So it's actually given by the Riemann tensor that these particles feel in this vicinity, with these two indices, beta and delta, dotted into the four velocity of the fiducial particle, and this index gamma contracted with this vector that we're studying. In other words, the acceleration or deceleration of this vector, the second rate of change of it with respect to proper time, is related directly to the Riemann tensor. Now, that's in fact a covariant expression, but let's try to express it in the coordinates of an observer, specific observer, who is at rest with respect to, say, this particle at the moment we look at this experiment. So a co-moving observer in an inertial frame sitting here and asking, how does this nearby particle behave relative to this particle? Now, who could such an observer be? Well, this could be an observer at LIGO at the beam splitter, where the laser beam is divided into two, goes down to a mirror and comes back, and we're asking ourselves, what does this observer, what is happening to the distance between that mirror and the beam splitter as a function of time as a gravitational wave comes by? How is that vector changing with time? So that's a practical realization of this sort of covariant abstract expression. Well, in the rest frame of the observer, the four velocity has no spatial component because your fiducial particle is at rest, so it only has a time component. So you just have R0, you have zeros here because U only has a zero component. C is a spatial vector because you're looking in space at that other mirror out there. So C has spatial indices. And you only want to care about the spatial component of X. Again, you only compare what that mirror is doing in space. So you end up with an expression for this spatial vector separating your two particles as a function of the spatial vector with this particular set of 6 components of the Riemann tensor. These are sometimes called the electric components of the Riemann tensor. Okay? And I gave you the formula for the Riemann tensor in terms of Christoffel symbols. You know the Christoffel symbols in terms of the metric. You know how to get the metric in terms of the Gothic metric, and you know how to get that metric in terms of the H's. It's all a set of things that you can do. Mathematica will do it for you in half a millisecond. And when you work all that out, you discover that the acceleration, the relative acceleration between these two geodesics is given by, it's related to H, the spatial part of H, but only specific components, the TT components. I'll tell you what that is in a moment. There's a half, and it depends on 2 time derivatives of this H. And remember, tau is always our retarded time, R is the distance to the source. But what are these TT components, transverse traceless components? So you get these components by defining a projection operator, which is a Kronecker delta minus a product of unit vectors in the radial direction from the source. So this automatically tells you you're looking at components that are perpendicular to the direction of the source. If the source is here, you're only looking at components in this plane perpendicular. And you also add to this a term that makes the trace vanish. In other words, if I contract on J and K, if I add HXX plus HYY plus HZZ, I get 0. So it's transverse. It's perpendicular to the direction from the source and has no trace. This tensor has no trace. Now, in this plane perpendicular to the direction of the source, it's a two-dimensional plane, so there's only, say, x and y components. So you have HXX, HYY, and HXY, and since H is symmetric, HYX is the same. So this leaves you with these three components. It turns out it leaves you with only two independent components. And so it's useful to describe the following picture where, so here this HTT is perpendicular to the radial direction and it has 0 trace. That should be an IJ, HIJ. So if the source is coming from the Z direction, all we care about then is the XY plane. There are only two independent possibilities for this TT field in that case. One possibility is where HXY is 0, HXX is not 0, but because of this condition, HYY must be the negative of HXX. The sum must be 0. But one possibility is that HXY equals 0. The other possibility is that HYY is 0, therefore HXX is 0 because of this condition, and then HYY is non-zero. So either this is non-zero or these are non-zero, and those are the only two possibilities. So there are 2 degrees of freedom in this gravitational wave. In quantum field theory language, these are the 2 helicity states of a massless particle, just like the 2 states of a photon. Photon has helicity +1 or -1, right? Any zero mass particle has only 2 spin states, plus or minus. And this is the same property. So there's only two specific helicity states. And I won't go through the details here. In GR, the spin associated with these states is 2, whereas the spin associated with photons is 1 times h bar. But these 2 polarizations impose a particular pattern, a particular behavior of these nearby particles. So let's suppose our fiducial particle is in the center of this picture, and the other particle, let's suppose there's a whole bunch of particles in a circle surrounding the center, and each one is moving on a geodesic. We want to ask ourselves, what does each of these sets of solutions do to this ring of particles? Well, let's consider this first. And remember the basic equation that the displacement of a particle is proportional to this times the location of the particle. Okay? So listen to this. Let's suppose that HXX is positive at some moment of time. It could be oscillatory, but let's let it be positive. So if HXX is positive, then this is HXX, then for a particle along the positive x-axis, its displacement is positive, right? So if a particle is on the positive x-axis, it moves outward. What about a particle on the positive y-axis up here? Well, HYY is minus HXX, so its displacement is negative. What about a particle on the negative x-axis? HXX is positive, but C is negative, so its displacement is negative. So this guy goes out and this guy goes out. this one comes in, and by similar argument, this one comes in. So what started as a circle has become an ellipse, distorted like that. Then half a cycle later, hxx is no longer positive, it's now negative. Maybe it's a sinusoid. So half a cycle later, it's all reversed. Instead of going out, particles here go in, and instead of going in, particles here go out. So half a cycle later, you get this pattern. Now, most of you, in fact, I'm completely sure that all of you are way too young to know what we used to do when I was a kid. Take a little piece of paper, fold it into 4, and fold it again into 8, and if you fold it over and the triangles, and in each triangle you gave a fortune and things, and you took that little piece, you're not that old, come on. Anyway, and you went like this, right? And you opened up, and then when you stopped, you flipped up, and you gave somebody's fortune, or you had whatever it was, little games. But if you can make that little thing, and if you're old like me, you know everything about gravitational waves. That's what's going on, right? You ellipse from here to here to here, back and forth. But you can see how it just comes out of the equation of geodesic deviation and the fact that for this particular mode, this is always the opposite of that. And by the way, there's no displacement in any angular direction because this is 0. So the particle is always displaced in the horizontal or vertical direction, but it's this. This is called the plus mode. And I think it's obvious why, right? This is the plus mode because this is like a plus. And you'll see this in the literature and discussions about LIGO. There's the plus polarization. The other one is when these guys are 0 and hxy is non-zero. Hyx, of course, is always the same. It's symmetric. So in this case, if you have let's say xy is positive, then if you have an object with positive x, then it experiences a positive displacement in the y direction. I have to start with a circle. So we've got the particle here with a positive x on the circle, but it gets a positive y displacement, right? hxy is positive. So the y of that particle goes up, half a cycle later it goes down. If I have a positive y particle on this circle, it gets a positive x displacement. So you can see a particle up here gets displaced along a 45-degree line. And then when the sign of hxy reverses, then this one gets converted into that one. It's actually the same pattern, just rotated by 45 degrees. In fact, that is an indication of why this is a spin-2 field, if you think in quantum field theory language. Because there are these general theorems that say that if you consider a state of a particle with a certain quantum mechanical spin, then it produces behaviors such that if you rotate by a certain angle, you get the same thing back again. So in an electric field, where the E field looks like this, and it's going up and down this way, if you rotate by 90 degrees, you get the same thing back again. Still the electric field pointing in the, say, y direction. Here, if you take this and, if you rotate by 180 degrees, right, you get the same thing back again. Here, you get the same thing back if you rotate by 90 degrees. Right, if you take this by 90, you get that. You're getting the same pattern. Nothing changes. The general rule it's kind of a phenomenological rule, I'm not sure who invented it, is that the angle that you have to rotate to get the same state back again is equal to pi divided by 2 times the spin of the particle. So for a photon, spin 1, the angle you have to rotate is, it's pi, I'm back engineering to get the right answer. So it's pi divided by the spin. Wait. No, it's actually pi. So I think I said that wrong. What I want to say is in the following way. For a photon, if you the two independent states of a photon are related by a 90-degree rotation, right? E field pointing in this way, B field pointing that way, or E field that way and B field that way. If you rotate by 90 degrees, you basically get the same thing. Here, if you rotate by 45 degrees, you get the same thing. Rotating this by 45 degrees, you get the same thing back again. So the rule is that you're rotating the system by pi divided by twice the spin gives you essentially the same thing you started with. So for a photon, it's pi by 2, B and E and B like that. You rotate by 90, it's E and B, so the same thing. Here, pi divided by 2s, pi by 4, 45 degrees, you get the same thing. If the spin is a half, it's a rotation by pi, right? You rotate the state by pi, you get the same thing back again. So it seems to be a rule of thumb that works, but gives you at least a handle on why these two patterns are related by this 45-degree angle. In fact, it had to be 45 degrees because what else could it be, right? It can't be 90. If you rotate this thing by 90 degrees, you don't get anything independent. It's exactly the same. The only independent mode that you could possibly get is 45 degrees. So these are the two states that you will hear people talk about, the plus and cross polarizations. And in LIGO, for example, you can imagine that having the arms, if the wave is coming from right above the LIGO gravitational wave detector, you want the arms to be along the x and y axes so that the movement of the mirrors is kind of maximized, right? Whereas that LIGO would not be very sensitive to a cross polarization because notice there's basically no motion in the x and y directions. The motion is in the 45-degree directions. So in general, of course, a gravitational wave would be a linear combination of those two polarizations, and what you measure will depend on how your LIGO arms are oriented compared to the wave coming in. And that, of course, is the kinds of details that people who analyze LIGO data have to think about. What kinds of polarizations are being detected? How can we be maximally sensitive to waves by orienting the arms in the various sites in a proper way, and so on. Any questions so far? But now I want to make a sort of an approximation to the lowest order of gravitational waves. What's the leading effect emitted? And so that means taking the lowest multiple. Remember, higher multiples sometimes involve higher powers of V over C. And so the leading multiple is the quadrupole, the L equals 2. We only care about the spatial part now. That's what gives the TT part of the metric. That's what's going to be observed by our detector. And so it's proportional to this TIJ. And we've already shown by using that identity that involves the Landau-Lifshitz and the mass density object, we've already shown that that's 2 time derivatives of the quadrupole moment of the source, evaluated at retarded time. So this is the dominant contribution to the signal from a source at great distance, just 2 time derivatives of the quadrupole moment, and it's these brackets denote that it's the trace-free quadrupole moment. So it's the quadrupole moment minus its trace. Namely, if you contract on I and j by summing over all 3 values, this just gives r squared, and you contract a Kronecker delta, you get 3, because it's just 1 plus 1 plus 1, and so you get 0 for the answer. So it's the trace-free part of the quadrupole moment that is the basic source for our gravitational wave signal. Here's what it looks like for just a system of bodies of some mass A and velocities A. There's a piece that has to do with their motions, V, Ij. So this is a product of V's, Vi, Vj, and then the gravitational potentials between them, again, with a trace reverse combination of vectors. Now, in gravitational wave physics, you may see this in later lectures when people talk about data analysis and the kinds of multiples that they detect and so on. It's become a convention to talk about this quadruple formula. It's the leading contribution to gravitational waves. It's sometimes called the Newtonian order result. It's not really Newtonian, of course. Newtonian theory doesn't have waves. Everything is instantaneous in Newtonian theory. But because it's the lowest order part, it just depends very simply on this simple Newtonian quadruple moment and its time derivatives. It's now become a convention to say this is the Newtonian part of the gravitational waves. This is only important because we have now over the recent years calculated corrections to this term called post-Newtonian corrections. By going to higher order and iterating those Einstein equations, you can calculate corrections, V over C squared corrections to the leading order. In fact, today, so you need to iterate 3 times in order to get the first post-Newtonian corrections and something called the 1.5 PN corrections. You have to iterate 4 times to go to 2 PN order. And I can tell you today that people in this business, mostly Luc Blanchet and his collaborators in Paris, are at 4.5 post-Newtonian order in calculating the gravitational wave signal for in-spiraling binary compact objects. Now you'd say, why should anyone want to do that? This surely is one of the most complicated things you could ever imagine, and I can assure you it is one of the most complicated things you could ever imagine. We have to do it because we're told by people at LIGO that we need it. LIGO data, the observations of these gravitational wave signals have become so precise, and one of the techniques used for understanding the signals and seeing if they agree with general relativity and using them to measure the masses and spins of the bodies is to use predictions of gravitational waves that are made by doing these kinds of calculations. And they started telling us in around the early 1990s, when LIGO was just on the drawing boards, that this quadruple formula, this lowest order piece, would not be good enough. They believed they would start observing these signals with such accuracy that to get reliable estimates of things like masses and spins and distance and other properties of the source, you would need more than this Newtonian piece. You'd need the first post-Newtonian correction. Well, it turned out that had been calculated back in the mid-70s by me and Bob Wagner when I was at Stanford University, but they said, no, that's not enough. We need at least a second post-Newtonian corrections. So people like my group at Washington University then, Luc Blanchet, Thibaut Damour, people around the world started calculating the second post-Newtonian corrections. We finally got those in the mid-1990s, and the LIGO people started saying, the way things are looking now, that's not going to be enough. We're going to need the third post-Newtonian corrections. And now, especially thinking about second-generation LIGO detectors with 10 times the sensitivity of the current ones and the ET proposed detectors in Europe, even 3 PN is not going to be enough, and that's why people have been pushing to 4 and higher order. So these are, I'm going to show some formulas in a second, but these are massive calculations driven by the needs of the experimentalists. So me, just from a historical point of view, I'm old enough to have been around at a time when general relativity was considered to be in the backwaters of physics and astronomy. It was not a serious subject for a scientist to pursue. In fact, my PhD advisor was told when he graduated from Caltech and was on his way to go to Princeton, he was told by a very famous Caltech astronomer, when you get to Princeton, whatever you do, do not study general relativity because it will never be important for anything. If you don't know, my advisor was Kip Thorne, so I'm very happy that he ignored that guy's advice and studied general relativity and became a leader of the subject. But the atmosphere between then and now has totally changed, and it's really this synergy between theory and experiment. we would have never considered doing these horrible calculations were it not for the fact that the LIGO people said, if we want to get unbiased estimates of the masses and spins of inspiraling binaries, we need these high post-Newtonian corrections, including the effects of spin, which I'm not even going to get into in these lectures. So here's what some of these things look like. Yeah. It's, zero, we call it 0 PN order, hence AKA Newtonian. I know that some people also just say 0 PN because it's kind of the leading term, the way Newtonian is the leading term in the weak field metric. So again, it's just terminology, but if everybody at least has the same terminology, you can have discussions and agree on what you're talking about.
But it's not Newtonian.
It's what, but as I say, Newtonian theory has no gravitational waves. So,
Sure.
So if you prefer 0 PN, go for it. I don't mind Newtonian. Give the guy credit, right? So, and of course, it's also important because it turns out that there's negative PN corrections when you deal with certain alternative theories of gravity, like scalar tensor. So it's a useful way to organize these orders so that everyone knows and agrees. Okay. All right, so here's just an example of what the gravitational waveform looks like, including higher post-Newtonian corrections. For a very simple case, a two-body system, a binary system in a circular orbit, so you don't have any modulations due to eccentricity. And here I'm just going to show the cross polarization, but there's a plus and a cross. Distance to the source, the total mass of the source. Beta stands in for V over C, so this is kind of the post-Newtonian expansion parameter, because V over C is always less than 1. But it's better to express it in terms of the orbital angular velocity, because that's directly related to the frequency of the gravitational waves, as you can see from these formulas. So this tends to be a non-covariant object, very coordinate dependent, but using this as your variable is somewhat more invariant, I will say. So, but anyway, when you see beta, it just stands for a post-Newtonian correction of order V over C. Here are the masses, the total mass, a reduced mass quantity, eta, it's dimensionless reduced mass. So it runs from very small values if the mass ratio is very small, if one body is very small compared to the other, and its maximum value is 1/4 when the two have equal masses. And then there's a dimensionless mass difference. So you can see that the general structure of these things is there's an H0, that's the 0 PN term, the quadrupole term. There's actually a beta cubed correction to that. Then there's a 1/2 PN order correction, linear in beta. So that's called half PN, or 0.5 PN. It's proportional to delta. So it only is there if you have an asymmetric system, bodies with two different masses. Then there's a 1 PN correction, beta squared. Then there's a 1.5 PN correction, beta cubed. It depends also on delta, and so on. And you can just keep going to higher and higher orders. So beta 4 is 2 PN, 3 PN is beta to the 6th, 4 PN is beta to the 8th. And if you look at these formulas, you can imagine how complicated they get as you go to higher orders. So at quadrupole order, and I'm just showing the cross terms, the frequency of the gravitational waves is twice the orbital angular frequency. And this is typical of a quadrupole perturbation. So that's all generally the case. So it's always twice the frequency of the orbit. But then when you go to the half order 0.5 PN correction, there are terms that are a sine of the orbit and 3 times the orbit. So you get higher and lower harmonics of the orbital frequency. Then the first post-Newtonian correction, these are, of course, these CNS are functions of the inclination of the orbit relative to the line of sight. So you get dependence on that. But then you get twice omega and 4 omega frequencies. Then at 1.5 PN, you get sine psi, 3 psi, and 5 psi. So you get lower and higher harmonics of all the orbital frequencies as you go to higher and higher post-Newtonian orders. Now, some of you may be worried, may have been worried all this time. I've seen worried looks on your faces, but I'm not sure why that is. But maybe it's because you're worrying about the fact that all my calculations have used flat space-time null cones, right? It had a flat space-time D'Alembert minus d by dt squared plus del squared. But gravitational waves don't propagate along a flat space-time. Space-time is curved. They actually propagate along a curved space-time null cones that are provided by the space-time in which they live. So haven't I made a grievous error by formulating this whole thing in terms of flat space-time wave operators? My waves are propagating with the wrong velocities, along the wrong null cones. What happened to the true null cones? Because space-time produced by this source is curved. This source curves space-time. What happened to that? Where'd it go? Well, here's where it went. It went into these tail terms. Remember, I talked about the fact that the gravitational waves can escape from earlier in the source, scatter off the space-time curvature that is provided by the source itself, and then reach us, but from an earlier phase of the orbit. And I said you could actually calculate these things in full detail within this framework. And when you do that, you get the following result. There's an additional term at 1.5 post-Newtonian order called the tail. And when you work it out for this circular orbit, looking at h cross, et cetera, the same conditions as before, you get this expression with this weird-looking term involves the log of the distance. And that just comes out of the calculation. You grind away, and there it is, pops out. What could that possibly mean? Well, if you think about it a little bit, I could combine the quadrupole piece, which is sine 2 omega, and this piece, which is cosine 2 omega, and if I change psi, and if I change psi by some small amount in each of these things, and then expand psi, maybe I could account for that term. So how do I have to modify psi inside here by some small correction so that I get sine 2 omega times cosine of a small thing, which is 1, plus cosine of 2 omega times the small thing? What do I have to do? Well, here's what you have to do. Just term psi from the retarded time that we've already talked about. This should be a small r. From our original retarded time, just subtract 2gm over c cubed times this logarithm from that. If you do that, then plug that into here and expand, you'll just cancel this logarithmic term. All this thing is a change in the phase of the original psi that we were using. What does this logarithmic change in phase represent? It's due to something called the Shapiro time delay. This is something discovered by Erwin Shapiro, a famous radio astronomer in the 60s. It's an extra delay in the propagation of a signal, say emitted from the Earth, traveling to a spacecraft and back, as it passes through the curved space-time of the sun. And this delay has become now important. It's important in pulsar timing. It's important in gravitational waves. It's important in gravitational lensing. It's important in black hole shadows. It's an extra delay because the light doesn't propagate along flat space-time cones. It propagates through curved space-time, and this is the effect of that propagation. So we haven't missed it, the effect of propagation along the true null cones of space-time. If you calculate enough and include things like tails, you find it, and there it is. So even though we started out with the wrong null cones, we get back to the true null cones for gravitational wave propagation by realizing at 1.5 p.m. order, there's a term that effectively gives us the Shapiro delay, which is what that effect is. This is kind of a beautiful realization that many of us made in this method, that we could really recover even the true propagation of the rays, even while starting with just flat space-time wave equations. But to get there, you have to go to high order. You can't just get it right from the start. You have to go to 1.5 post-Newtonian order. And of course, as our colleagues working at these very high orders 4pn order have discovered there are tails of tails and tails of tails of tails, and there's all kinds of nonlinear higher order effects that arise. Now we have waves propagating to infinity, and you remember we had a formula for the energy of our system, and we could relate that formula to the flux of waves through a surface surrounding our source. So let's return to that. The rate of change of energy is d by dt of this tau 0, 0, this complete energy momentum object that includes matter plus the Landau-Lifshitz and harmonic pieces. That becomes a divergence of tau 0j, and that converts into a surface integral of T Landau-Lifshitz 0j. The harmonic term doesn't produce anything, it turns out. And this, when you work it out, plug in, remember, T0j depends on derivatives of the Gothic metric. We have formulas for the Gothic metric, plug them in, grind some more, and when you're finished grinding, you grind a little more, and you finally learn that this result, this rate of change of energy, is the square of the d by dt of h plus the square of d by dt of h cross, the two modes that were in our gravitational wave signal. And if you plug in what these things are from our gravitational wave signal, you find that it's 3 time derivatives. Remember, h plus was 2 time derivatives of the quadrupole moment, trace-free. So there's another time derivative. And when you put all this together, it's 3 time derivatives of the quadrupole moment, trace-free. It's quadratic, obviously. And then you contract on the 2 pairs of spatial indices. And there's a factor in front that you calculate. And these, of course, are higher order corrections. So this famous formula is called the quadrupole formula for energy flux. And again, it's also known as the Newtonian order contribution, or the 0pn order. And using the same method, you can calculate the flux of angular momentum from, say, a binary system, and the flux of linear momentum as well, using similar approaches. Ironically, this formula, this quadrupole formula, was first calculated by Einstein in 1916. Einstein felt that his theory would predict waves, because after all, he built it on the foundation of Maxwell's theory. He knew Maxwell's theory inside and out. He built it to have some kind of Lorentz invariance, and whenever you have Lorentz invariance, you have a finite speed, and therefore you have waves. So he was sure that his theory would have wave-like behavior. And so he asked, what would be the waves emitted by some laboratory object, like a big dumbbell that you rotate like this? So he did that calculation and published a paper in 1916. Then his colleague Nordstrom pointed out to Einstein that he made several grievous errors in his calculations, few conceptual errors, few mathematical errors. Everybody thinks Einstein was perfect, but he made mistakes like any other human being. And so Einstein published another paper in 1918 correcting the errors that Nordstrom had pointed out to him. He still was off by a factor of 2 because he made just another stupid little error. That was pointed out by Eddington in the 1920s. But overall, it was the same formula as what I've shown here. Okay? During the 1970s, people started to ask the question, this is true for a dumbbell, an object held together by gravitational forces. And Einstein used purely linearized theory to get this calculation. He didn't think about all the higher order, the Landau-Lifshitz stuff that we've been talking about. It's pure linear GR. But people started to think, well, what about binary systems? In linear theory, linearized GR, binary systems don't even exist. In linearized theory, bodies don't even interact with each other, at least formally speaking. So is there some difference? Do binary systems emit waves differently than you would get for just an ordinary laboratory dumbbell? And it turns out, of course, the calculation has to be very different, because you notice we had to take into account the Landau-Lifshitz pseudotensor to get the right equations of motion for matter. Right? They're moving under gravity, so there has to be gravity inside the system to produce their motion, otherwise they just move away on straight lines. So gravity played an essential part, but along the way we had this little curious identity that allowed us to convert tau ij, which had matter and gravity, into some time derivatives of the quadrupole moment. And at the end of the day, we ended up with exactly the same formula as Einstein got in 1918. And that has confused a lot of people over time. You'll see textbooks that say that to get the gravitational waves from a binary system, all you need is linearized theory. And it's simply completely wrong. And I rail against people who write these textbooks and make these statements. The point is that in Einstein's theory, in Einstein's calculation, there's a difference between the meaning of dot and the meaning of it in our case. In Einstein's equations, dot means apply the equations of motion for a dumbbell, which are equations of motion that have no gravity. They have physical stresses that hold the dumbbell together, right? The metal and the glue, these are non-gravitational forces that keep the dumbbell, big balls of the dumbbell, going around each other. So dot means use equations of motion for dumbbells. But the dot in our case says, in this case, this is the lowest order, it says use Newton's equations of gravity for the motion of your two bodies. And that's very different. So you have to go to nonlinear order, at least to one iteration of Einstein, to the second iteration of Einstein's equations, to get this lowest order quadrupole formula. Even though it looks the same as Einstein's formula, conceptually it's not the same thing at all. Anyway, so here's what it looks like for a two-body system in terms of the orbital variables. This is the square of the velocity of the orbits. This is just the radial part if you have an eccentric orbit, so they're getting further and closer together. So it's a very nice simple formula for EDT, this for the simple binary. You can take that and average that rate of energy loss over one orbital period. So this is averaged over an orbit. So it depends on the ratio of the mass to the semi-major axis of the orbit, half the major axis, times a function of the eccentricity of the orbit. E equals 0 is circular, but E could be as high as 1 for a very elongated orbit. So there's that function here, and some just factors to get the right dimensions. If the system loses energy, then its semi-major axis must change because E is proportional to 1 over A at Newtonian order. And if the semi-major axis changes, then the orbital period must change because they have a direct relationship via Kepler's laws. So basically, any change in E causes a change in orbital period according to that relationship. So for a binary system of two stars, dp dt should be negative, the period should decrease, with a factor here, m, which is proportional to the total mass and this dimensionless mass ratio quantity. This is sometimes called the chirp mass. It's a mass that you'll see all over the place in gravitational wave calculations. And it depends on the period and this function f. And of course, why this formula is important is that, so I said most of this, it's Newtonian. So we've done a very high order in these corrections. But of course, it's important because of the discovery in 1974 of a binary pulsar, a pulsar in orbit about a companion neutron star, as we now believe. And the system is so relativistic that its orbital period decreases because of this loss of energy to gravitational waves. And this is a plot of a quantity related to the orbital period. It's called the time of pericentric passage. And if it should decrease quadratically with time if there's this dp dt. And the points on this graph are the data observed from 1975 to the discovery till about 2005. And the curve is the prediction of general relativity for how those times should evolve with time. And even the error bars on this graph have been magnified by a factor of 400, just so you can see the observational error bars. But the agreement with the prediction of general relativity is now at the level of 0.02%. So it's a great prediction of the general relativity confirmed by Hulse and Taylor. And for them, of course, it meant the Nobel Prize in physics in 1993. Yeah, sir? I said Cliff. I'm sorry. Right, so I'll say a little bit about this. The counting is different if you're looking at the equations of motion. So this is 0 pn in the flux, in the waveform, but in Newtonian theory, of course, Newtonian theory is zero, and this occurs in a post-Newtonian expansion in the near zone at 2.5 pn order. So I'll say a little bit about this in a few minutes. Where does this come from in terms of the near zone interactions? And what is it that makes this orbit decrease in period? There must be inner forces inside the system to make the orbit decrease. I'll talk about that. But it's a 2.5 pn order within the equations of motion. Okay, so I just want to show one example of what these kinds of formulas look like when you really get serious about going to higher post-Newtonian orders. So this is an example of the energy flux. This is from review by Luc Blanchet on Living Reviews in Relativity. So I use eta, he uses nu, and I've been arguing with him for years to switch to eta, but he refuses. You know, those French are so stubborn, you just can't get them to change their minds. So anyway, so nu is my eta, same parameter for this x is this beta to the 2/3 that I talked about. So 1 is the quadrupole formula. The first term in this expression, that's the quadrupole formula that I showed you earlier on in this notation. But here's the first post-Newtonian correction. So x is beta to the 2/3 or v over c squared. So that's 1 pn. There's 1.5. This is the tail term. That's how it affects the energy flux. That the tail term, Shapiro delay term, gives you this little term in the energy flux. Here's 2 pn. So this was calculated by me and Wagner in the 70s, but independently, Blanchet and Thibaut d'Amour and others, and my group at Washington U calculated these 2 pn terms in 1996. Then there's 2.5 pn terms. Again, these are tails. These are post-Newtonian corrections of tails. Then there's 3 pn. This horrible thing. I mean, look at these numbers. I mean, and different groups calculate these things, and they get exactly the same answer. When we did this calculation in 1996, my group, Alan Wiseman and Larry Kidder, were a little behind Thibaut and Luke, and we were about 5 months behind them in getting the answer, but we had agreed we would not interact with each other at all until we were completely done with this expression. And then we would compare and see. We didn't want to steer each other in one way or the other. But this is 1996. You just couldn't send a PDF by email. We had to send, you've heard of this thing called a fax? So we typed up our formula, faxed it to Paris, and because of the time difference, we had to wait till the whole next day for them to get it, read it, and check. Finally, we got a fax in return, and it said, and the fax said, we agree, term by term. Everything's in agreement. So it was one of those moments in your career where you think, this is all worth it. Oh, and of course, as I've tried to emphasize, these are calculations. They can be done and reproduced. This is not phony stuff. Anybody can do this and get the same answer. And of course, at these higher orders, different people have done different things. And again, complete agreement, term by term. But it's also pretty horrible. So you have to have a certain amount of stamina. Yet, on the other hand, Maple and Mathematica are absolutely essential to doing these kinds of things. So a lot of the steps are automated. Okay, what happens to make the orbit of this binary pulsar damp? We have energy flux at infinity. How does the orbit know that? How do these two stars have their orbital period decrease? How do the two neutron stars or black holes ultimately merge when this energy flux is going to infinity? So that loss of energy to infinity must be accompanied by some sort of forces within the system that that affect the system and cause some irreversible behavior to occur. And that's really exactly what happens. This loss of energy implies that the system can't be conservative. It can't have a conserved energy. Its energy must decrease at some level. And so there must be a force that dissipates energy in such a way that if you take that force and dot it into a velocity, that gives you an rate of energy change. There must be a way that that works and then gives you the energy flux at infinity. So one can define this, go back to the near zone, iterate the relaxed Einstein equations. You have to do it 3 times, not just 2 for the lowest order. We have to do it 3 times. And this gives us the metric to 2.5 post-Newtonian orders. So you have to go to 2.5 pn order in the metric in the near zone to get the 0 pn energy flux at infinity. It's a bit of a mismatch in counting orders, but that's just the way it is. Then you get this term, you insert it, and you can calculate the post-Newtonian corrections. And focusing on the 2.5 pn corrections, you can get the radiation reaction. So here's roughly speaking how it looks. In the near zone, you remember we were expanding in powers of this kind of a quantity. So H00 has the Newtonian, kind of a Newtonian piece, a regular potential. Then there's a term that involves this x minus x prime in the numerator. Remember, it's a power series in this thing with 2 time derivatives. So this is a post-Newtonian correction. This is called a superpotential. Then there's something with 3 time derivatives with this squared, 4 time derivatives with this cubed. This is called a super-duper potential. And then 5 time derivatives with this to the 4th power, and so on. You can just keep going. This, of course, is just the Newtonian plus all kinds of post-Newtonian corrections that you have to build into tau 0, 0. You just have to work out a lot of details. There's no term with a single d by dt, because it turns out that's just d by dt of the mass of the system, which is 0 up to high order because of conservation of energy. This is this superpotential. So one first post-Newtonian correction. This turns out this is purely a function of, this can be shown to be 0 or a function of time that can be thrown away by a certain gauge transformation. This turns out to be irrelevant. This is a second post-Newtonian term, but here is the term that we really are interested in. It's a 2.5 post-Newtonian term. Notice that has 5 time derivatives of the object. So one of the things you see from that is this is a non-time symmetric term, right? Turn t into minus t, and this term changes sign. So it can be a dissipative term, right? It's not conservative. So this term is responsible for a net change in the energy of the system. This one was also odd, but for various technical reasons, you can just show it has no effect. So this is the first one that actually has an effect. And so when you work all this out, I'm not going to go into the details, you find a force at 2.5 post-Newtonian order, and when you work it out for a 2-body system, you get a radiation reaction force, 1 over c to the 5th, that's the 2.5 pn term, depends on velocities and separations between the 2 bodies. And you can manipulate by changing coordinates a little bit into a slightly different potential, but the key point is you get expressions for the force within the system that causes its energy to decrease. And then you can verify, using either this version or the version on the earlier slide, they're just related by a coordinate transformation, you can verify precisely that the forces within the system that cause its orbit to change exactly agree with the energy loss that you calculated for infinity, both energy, angular momentum, and linear momentum. So there's a perfect balance to this order of approximation between what you measure at infinity for the loss of these quantities and what you calculate within the source for the loss of the same quantities. There's a kind of a balance between the two, which is certainly reassuring that there's not energy being stored somewhere between the system and infinity in some weird way. You can also take averages of these things in terms of the orbit elements, the semi-major axis A and the eccentricity E of the orbit. And here I'm using something called the semi-lattice rectum, which is a specific combination of these two things. It's related to the orbital angular momentum. And here are the expressions for dp dt and dE dt in terms of the orbit elements, E, gm over p, and so on. The key point is that dE dt is always negative. So gravitational waves cause the eccentricity of the orbit to decrease. So gravitational waves tend to circularize orbits. So you can start with an orbit that's highly eccentric, and by the time they're close enough together to merge, the orbits are almost perfectly circular. In some ways, this has been very lucky for gravitational wave detection, because having eccentric orbits makes the gravitational waveform much more complicated than for circular orbits. And so it's in some ways lucky this effect occurs, so that the first detections could be made with rather simple predictions for the gravitational waveforms, namely those based on circular orbits. Now, of course, data analysis is getting better, and LIGO is explicitly searching for the added effects produced by residual eccentricities in orbits. Very difficult problem, but they're now able to address those that possibility, and theorists are now starting to develop waveforms with eccentricity. But in some ways, it's lucky that they're very, very small, so at least you could start the detections with circular waveforms as a good approximation. So for example, this famous Hulse-Taylor binary pulsar, the change of its eccentricity hasn't been measured. It's very difficult to measure, but we have certainly measured the decrease of its orbital period, and you can estimate that it will circularize and merge into probably a black hole in about 300 million years. Another related system called the double pulsar, discovered maybe 20 years ago, that will merge within 85 million years ago. And the reason this is an important number is that this is short compared to the age of galaxies such as the Milky Way, which are measured in gigayear timescales, billion-year timescales. This means that there must be neutron-star binaries merging today, ones that started their life early in the galaxy that are merging now, because they only live a short time, 300 million years, and even neutron-star black hole and black hole binaries. And of course, this conventional wisdom that was emerging in the 1990s became part of the science case for LIGO, that things like the binary pulsar told us that we could expect these kinds of binaries merging today and maybe detectable by the LIGO that was being proposed with a price tag of a couple of $100 million. So it was important to have this kind of understanding that these things might be interesting sources of gravitational waves. And of course, the actual detection of these things. Now almost 100 cases of black hole binaries, several neutron-star, double neutron-star mergers, and a couple of confirmed and semi-confirmed cases of a mixed merger by the LIGO-Virgo-Kagra collaboration has confirmed this basic picture that these things can evolve quickly enough that you can see them in distant galaxies today. Of course, the big surprise was that back in the 90s, we all expected neutron-star binaries to be the detectable objects. They were the only things we knew about. At that time, we knew of binary pulsars, but nobody knew about black hole binaries. And there was almost no evidence of neutron-star black hole binaries from, say, X-ray astronomy or gamma-ray astronomy. No one knew if these existed or what their rates might be. But you could, one had a pretty solid idea there'd be neutron-star binary mergers. So that became the science case for LIGO. But it was a great surprise, of course, that the first detections were black hole binaries. And the reason that was such a surprise was that back in the 90s, we assumed that black holes came with masses of between 6 and 15 solar masses. In fact, no one believed that you could get a black hole more than 30 solar masses based on supernova models and so on. Forget the supermassive ones, we all knew about those. But black holes should be between 10 and 15 solar masses. But of course, the initial detection, 1509-14, the black holes were 30 solar masses, way higher than anyone ever expected. And that's been a big surprise for both gravitational wave detection and astrophysics, finding out how you get such very massive black holes that they've now detected mergers with 80 and 90 and 100 solar mass black holes. So that's been a shock to the system. And of course, aside from the fact that I'm old enough to know about, recall a time when astronomers were very strongly opposed to LIGO because they felt it was just a physics experiment. It would only detect gravitational waves, which you already knew from the Hall-Taylor binary repulsor. We knew they existed, and there was nothing else you would discover. But as soon as, in particular, the black hole binaries were discovered, astronomers were shocked at the size, the masses of these things. And then when the first binary neutron star was detected and produced a kilonova, then the astronomers really came on board because this was something that helped understand where platinum and gold came from in the universe. The electromagnetic emission from this system was completely new, something no one ever expected. The nature revealed secrets about these binary systems. So it made me feel really good that when I once testified before Congress with an astronomer beside me testifying against LIGO, I was testifying in favor, to see the detection paper for the double neutron star binary having almost all of the world's astronomers as co-authors of that paper. So it made me feel good that they really do accept gravitational waves as something important to them and not just to physicists. Okay, so I've tried to give you some theoretical introduction to gravitational waves. This is pure theory. This is trying to get you to understand where we think the gravitational waves come from, what is it about general relativity that allows gravitational waves to exist, but more importantly, how does one calculate real gravitational wave signals from real astrophysical sources? I've tried to give you the method that basically is the go-to method these days for calculating waves, at least from the in-spiral part of the binary merger. Eventually, the two stars get so close together that these kind of weak field methods I've described, post-Newtonian methods, no longer work, and you have to resort to full numerical relativity calculations to get the merger part of the waveform. And that's fair enough. But what a big surprise that we've learned in this is that the post-Newtonian calculations match onto the numerical relativity calculations much more smoothly than we ever had a right to expect. We know post-Newtonian theory fails when the fields get too strong, but even in a regime where the fields are starting to get so strong that you'd never believe post-Newtonian theory, the predictions smoothly match to the numerical relativity waveforms so that you can get a complete accounting of the waveform from start to finish, and that's been crucial for data analysis at the LIGO detectors. So that's been kind of another surprise for many of us working in this field. There's a famous statement by Eugene Wigner about a paper he wrote once on the unreasonable effectiveness of mathematics in the physical sciences. It's sort of an interesting question. Why is mathematics so powerful in physics and chemistry and so many other fields? So he wrote a whole essay, interesting essay, just on why is it so effective. So we in this field talk about the unreasonable effectiveness of post-Newtonian theory in gravitational wave physics. It's much more effective than we had a right to expect. And so it's through these methods that then you can do your calculations and really start to interact with experimentalists and find out what they observe, what they need, and what you can do to participate. Thank you. Questions? Happy to have questions. We have to get out of here at 5, right? Or head for the doors at 5. Okay, yep. Sorry, Steph? What are the inputs? Sort of the physical inputs, or yeah. So if we're treating, the leading motivation, of course, is compact inspiraling binaries. Right. So the physical objects are neutron stars or black holes. In a lot of these calculations, we tend to treat these things as bodies that are so small compared to their separation that you can ignore their finite size and basically treat them as delta function sources. In fact, that's illegal in general relativity for various technical reasons, but there are ways to get around that. One is by various approximations, just expand things in powers of the ratio of the size of the body to their separations. There are various regularization schemes that people have imported from particle physics to use delta functions, but then regularize the inevitable infinities that occur in a systematic way, just as you do in quantum field theory. And these have all been very effective. But basically, we ignore the internal structure of the bodies to a large degree. For black holes, it's sort of the same. We don't care about the fact that space-time is so curved that there's an event horizon, because all we care about is the relative motion of the two black holes in a regime where the effect of one on the other is weak. Okay. What's going on here is, it doesn't really matter until they're so close that you just have to hand it off to a numerical relativity expert and run the full Einstein equations with a big code, and then try to match the two approximations. But the underlying idea is we have bodies whose internal structure doesn't matter until you talk about spin. If these bodies are spinning, then you have to start to deal with that, because angular momentum does add complications, but this has been part of the process with post-Minkowski theory for many, many years, and people have been calculating the spin corrections at various p-n orders as well, again, because LIGO has marginal information about spins of some of the mergers, but with next generation LIGO and ET, they'll be measuring the effects of spin like crazy. So we really need to have the predictions locked in. Okay, well, tomorrow, I think it's just after lunch. For those who wish, we'll just do a few simple exercises based on what I've said. I think I'm probably going to have everybody calculate the 5 p.n. corrections to the waveform. No? Somebody doesn't want to do that? Okay, we'll do something maybe a bit simpler. Anyway, we'll do some stuff tomorrow just to give you some hands-on experience with some of this.